So today we'll start a new kind of flexures, and we call it a whole flexure. So I think the picture you have here, I think it's a self-explanatory. So why it's called whole flexure is basically you drill two holes and make the section there thin enough so the flexure behavior, the bending is possible at that point, and that's why it's called whole flexures. So you remove the material selectively. So I think it should be very clear now. So and so it's just like this, right? So you have hole, okay, all around, and then right something like this, and again on this side. It can be long enough, and then you can go in the dimensions, right? So clear now? So if you apply any force here or moment, see this is the axis I'm talking about here in 3D. So this is the point we are talking about, and usually this you don't remove the material, so you just drill a hole and then make a cut here. So that helps in protecting the flexure also. How? Because in this case the elastic range of motion is very limited and maybe the order of few degrees only. So many times it's only is even less than one degree what is saying. But okay, you can get you can go for higher numbers, but okay, then you have to understand why it's there, and there will be some kind of nonlinearities, and maybe the stresses will be too high and it can fail or it can yield. So you may not want to have. So, but adjustment of this order might be very important when you are going for some space application or optics, or suppose if you have to adjust some optics, some lenses. So, and suppose for astronomical application, space applications. So where you want to target something, maybe in light years you are talking about, right? Or millions of kilometers. So in those cases, even this kind of adjustment is required. So when you are building telescopes, high-end telescopes, you have to adjust the mirrors. So one is okay if you have to get a very accurate mirrors, but at the same time you also need to adjust later, because you cannot have a huge mirror, so you fabricate a smaller pieces, but then you assemble and then adjust it, and the adjustment requirement will be of this order. But shortly you'll see that there are a lot of applications, and even in day-to-day life it can be used. So the idea behind this one, so you just drill two holes and then you get the thickness. So what is important here is the thickness here, so which is h, the diameter of the hole. So these are the two key parameters. So whenever you have to design this, you have to look for this. So what is the thickness of the hole flexures and what is the diameter of the hole? Not necessarily you have to drill the entire hole, but it can be some angle alpha might be good enough, right? So suppose if you are going for unconventional machining, or suppose deposition methods or 3D printed kind of application, even metal 3D printing this you can do, you may not have to go for drilling, right? So then you just go for this minimum alpha, right, which gives you this behavior. And then in this case what is there is, okay, in third dimension, the thickness is, you have the thickness, enough thickness, so that you get this stiffness. So if you have this torque psi, and then you have this rotation, that is the degree of freedom. The constraint directions are, of course, this x, y, and z. All the three translation are constrained. This rotation is like phi is also constrained. Psi is degree of freedom you have, and theta is also constrained. So only one dot. So it acts as a hinge. So again, so there are a lot of work done, and I think we just use the charts, or there might be some empirical relationship, but the chart is good enough for initial dimension. So I just make the outer edges so that it's apparent, right? So it's something like this. Clear? Yeah, so this is your hole hinge, and if you have so from this chart, what you have realized that, just let me, yes. So this is not linear, and here there are two parameters, h by d ratio you are talking about here, h by d, and one is square root of h by d. So h is the thickness of the hinge, and d is the diameter of the hole, right, or the projected diameter. With respect to that, so this is the physical dimension, physical parameters, and along the y-axis you have different parameters, the mechanical behavior, right? So what you will be interested at is what is the stiffnesses in different direction, yeah, and the and the stresses and the strain. So one very important is k psi, right? So this is the rotational axis, right? So along this axis it will rotate. So what is the rotational stiffness? So this is not directly there written, but it's a normalized, some kind of normalized, that so that all these parameters can be shown in one chart itself. So here 12 k psi divided by ETH square. So with respect to h by d or under root h by d. So I think this is from here you can, E is the Young's modulus for the material, T is this width of the flexure, and H is the thickness of the hinge, right? So depending on whatever dimension you choose, you will get this number. So you can select from this chart. So usually in the exam or in any project also, if you are doing, you can use this chart to do this calculation. So this is very important. Yes. Another is, so this is one parameter. So talking about the rotational stiffness. So this is rotational stiffness. What will be the unit in this case? If we are talking about SI units, anybody? Jisnu? What will be the SI unit for the rotational
Sir,
stiffness? How you define the rotational stiffness?
so taught by the angular deflection.
Yes. So if I just ask what will be the SI unit, then what will be the units?
Newton meter itself.
Newton meter per
Radian.
radian. Yes. So I think you have to
radian
be aware.
means.
If it's in degrees, then you have to convert into radians, right? So I think whenever you do the calculation, it's very important that you convert into right SI units and then do the calculation. Otherwise, you can create a big mess. Okay, so be aware of that. Always work with the SI units. It's very important. No matter what, whether it's small or big, start with SI units. Right, 10 to power 9, 10 to power minus 5, 10 to power minus 12. If it's there, just write it. But at the end, at least you will be comfortable. You don't make any mistake. Otherwise, what will happen? One will be in Newton per millimeter square, one will be in millimeter, so you don't know. Some will be in millimeter, some will be in meter, and everything will get messed up. Okay, so convert everything in SI units and do the calculations accordingly. So one key parameter we'll be looking at is this rotational stiffness. What is also important? The stresses and strain, right? So when you are rotating, what is the bending stress, right? And this is the strain, right? Agreed. Hmm? So this is, and this sigma, how you will get? So either you have to do all the calculation for the material, whatever material you are choosing, right? What is the different kind of loading, and from the loading, what will be the stresses developed, right? And for the chosen material, what is the allowable stress, right? So if the allowable stress is given, then you will be able to also find what will be the maximum strain, right? From here, a maximum strain will also give you the maximum rotation. What will be the rotation, right? So here I think it's directly talking about the rotation part, right? Shy. So what will be the range? So range you will get it from here, for the given material. So E will be known, sigma will be given. Either you will be is calculating yourself, or it will be given what will be the allowable maximum stress, right? And from that you will be able to find what will be the rotation possible, right? So the maximum, so that will give you the range. One thing you have to also realize that it's a plus minus, right? It's a plus minus. So if it's bending from here, suppose, and this is the pivot kind of thing, it can flex to either side, right? So call it plus and minus. So it will give a range to one of the sides, right? So suppose this shy you are getting is 5 degree. So total will be plus minus 5 is total is 10 degree, right? Be aware of that. So many times the calculations, in the calculation you have you can be tricked. So that's the one part. That's the important. Now CXX. This is the stiffness along the translation direction X. Similarly, CZ, these are all constant directions. So bearing stiffnesses, right? CZ, Z. What else will be required? Here also, okay, you can calculate forces and you can calculate the torque. But anyway, I think if that is required, then you can use this formula, right? The stresses are given, and then so for the dimensioning, you have to use this chart. So this chart will be provided. So very nice example here. Can you identify what it is? How it will work? Can you identify the functional or the features, functional features in this design? Anybody?
So two plates relatively bend to each other. Like
Sorry. So suppose
relatively
if I fix this part, and if this force is applied, what will happen? If I apply force at this point and I fix the base, what will happen?
but if we applied force in perpendicular direction, then it can go inside it. Not in linear direction. It have little flex in
So,
that direction.
so assume that the thickness in this direction is thick enough. Is thick enough. So suppose some thickness in there. Good now. It's a three-dimensional thing. And suppose now I'm applying a force here. Suppose this is I call it X, Y, and Z. So suppose I'm applying force Fx in the X direction, and negative X direction here on the upper part. What will happen? Anybody can visualize that? Anybody?
It can move slightly in the X direction, and I think that
Do you think it will move in X direction?
yes,
Negative
it will.
X direction? Yeah, if I means in the direction of the force.
Yes,
Okay. What happens if I apply a force in Y direction?
Y direction. It will move also move in Y direction
Why?
because in the center there are two holes, and that it will. Uh,
So what you see in green is something which is just you extrude. So there is enough width also. This width is good enough, I would say. This called B. So see, essentially what you see here is, okay, I think maybe a next question. What will happen if I just remove this material? Do you think it will create any problem if I remove this material? What I have here, I just shaded.
no, sir.
It will not. What happens if I remove this material as well? Do you think it will affect?
Not sure, sir, about this.
So actually here what you see is essentially this is as good as you have the base and you have the upper part. Okay. And what you have is what we just discussed is about pivot hinge here at these points, right? It can rotate at these points, right? You agree, right?
Yes, sir.
So it means there is a revolute joint here, hinge here, there is a hinge here, there is a hinge here, and there is a hinge here. is connected here, is connected here. The middle section is thick enough, right? This part, these are thick enough. So they will only bend at this section where you have the holes, right? Otherwise it will not bend. So it will be just like two links. So it's just like a link, rigid link. Agree? What it will look like now. So it's just a link here, rigid link, and with the pivot joints here. Do you agree that the working principle will be same?
Yes, sir.
So just
But
if
excuse
this
me, sir,
B
sorry.
is, if this B is high enough, then it's just a planar mechanism. It just moves in a plane. What happens if you now apply a force F here? It will move in this direction. So it can only move in this direction. Y direction it will not move. Z direction, of course, there will be some motion, but that will be parasitic motion. Because of these hinges, and these are flexure hinges, actually you can equivalently replace with a kind of torsional spring here. At each joint, it's a revolute joint with the torsional spring. With the stiffness, K psi, right? That's what we just discussed, rotational stiffness. Do you remember here? We are talking about K psi. This is rotational stiffness. Agreed? Do you experience the same stiffness here? Now is for you to now understand. It's now just a parallelogram, right? It's just a parallelogram, nothing else. Four links. This link is fixed. This link you have the shuttle, right? This link was simply fixed. And all the revolute joints are having some torsional stiffness, assuming they are all same. So what will happen if I apply force F? There will be movement delta in this direction. If it moves by delta, what will be the strain? What will be the rotation? So it moves by delta in this direction. It moves by angle this, and this is equal to delta, right? So if it's very small, what will happen? If this is P, delta will be P times. Agreed? So again, you can find psi. What is the rotation? What is the range? And if you know that, you also know what will be the allowable displacement. What will be the displacement allowable stiffness in the x direction. For given range, if you know this K, you can also calculate what will be the maximum force. What will be the force? Actuator force, right? You want to move in that direction, right? So I think if you think and try to understand, you realize that everything is there, and you can, if you are able to break it down, you can though you have a chart for just one hole fractures, but all the information required here to design this one is there, right? So I think practice, and I think this is definitely there will be one question in the exam around this. So if we just try to work on this problem, this is from the book, and you can check it also yourself. So what is saying that if the displacement required is 0.5 millimeter, and this is of force F, thickness T is along that direction, in the weights we are talking about. P is the distance between the your hole flexures, that is given 40 mm. D is the diameter of the hole. This is what you give, what is given, sigma max allowable for the given material for 400 MPa, and the E is Young's modulus, that is also given. And now suppose if you have to design, how you proceed, although answer is given here, but may not, may not be a single answer for this. Okay, so try to do the calculation on your own and find it. Now I think what happens is, okay, what is the relationship between this H and D? Which one you should use? What is the ratio, right? And what will happen in the extreme cases? So here in this case, the D is too small, right? So H by D, relatively high. So if it's very high, then what happens? CZ and CY in both directions, the stiffnesses are really high, right? And they will be equal. But if you this H by D is small, so it's like a neck, right? Of course, then CZ will be relatively small compared to CX and CY, very small. And but when you design these kind of things, I think in previously also when we are talking about the uh, uh, leaf spring or the hinges using just sheet flexures, we are also talking about this force and the orientation of the forces, the predominant forces. What will be the orientation, right? So because if you have forces in z direction, there will be shear, and it may not be, the stiffness may not be high in the z direction. So we always try to use this concept, and sometimes we are not very sure, so then we use cross design. So this is the design I just mentioned in the beginning of the class, when I was showing you some figures. So, and that's why I asked, just make one SolidWorks design and pass it to me. So you make cross pivot using hole flexures also. That's also possible. This is a very good example. This is a linkage design, and you can say it's just a concept. And what is expected? Can you design a mechanism based on this concept? So what is there is, if there is a force applied here, and there is so what it says, convert this idea into correct notch. So the whole flexure is also more or less called notch mechanism, right? So the right hand wall is fixed, this wall is fixed in this case. So this is fixed wall. Blue part is adjustable by a screw. So this is a screw. Try to understand the mechanism. Okay, the screw in the height direction. So in the height direction, in this direction. But the screw is in this direction, right? The blue part also has to sustain an external force. This is external force. So this is the mechanism. The force is there, or maybe you call it a weight in vertical direction. F is coming, but through this screw you can adjust it. How? Huh? Anybody? Do you think it will work? Anybody? Nobody? So again, this is pivots here, right? What you see here is a very thin strip here, huh? And virtually, if we have such mechanism, it's pretty much sure that the forces in this case will be in tension. So it means you can use even wire cables, and that's why it's very thin section. But essentially, okay, it's a 4-bar mechanism, parallelogram mechanism, and there is a threading here. So screw here, thread, and okay, this can just, so when you push this part, they will get pushed against each other, right? This blue and the light blue one. So what will happen? Because of that, it will try to rotate. So then in that case, it may move up and down, right? So it can go like this. So then this thing can go like, right? Or, and it can go like this. So do you agree now that this may work? This can work because this can go like this and this, right? So because the light blue thing will be able to rotate, and because of that, although it looks that the adjustment is in the horizontal direction, but how is possible that it can adjust the dark blue box in the vertical direction? So do the analysis. Very nice mechanism. Now the next question is, suppose if you have, or you can, some of you can just design this. Very nice. What will be the whole flexure? So you know that is just a parallelogram mechanism. Right? This is what is required here. But why we are concerned that, okay, means if you are not aware of that, what you will do? What will be the orientation of the flexures, whole flexures? Suppose I can just make hole in any direction. How does it matter? Right? Wherever hinge is required, in the previous example, yeah, it was like this, right? Why we are talking about this case, right? So I think just now we talked about this predominant directions, F, right? And suppose if we know this the force direction, it will help us to orient. And that's the idea. So if this is the case, and suppose now if you do the force balance, so this is the case now. So if you apply force F, how it will get balance? So you have to do the free body diagram. If you do the balancing, you will know that what kind of forces will be required there. Okay. So this is how you proceed. So first you have to find the forces at the pivots. Once you know, so these are the directions, nature. And from that, since here I mentioned that in this case the force direction will be along the axial direction only. See? So the flexure orientation will be simply in the normal direction. So that's why if the force direction is along this way, in this case you just put the whole flexure like this. In this case, it's a little diagonal. It's a diagonal. So along the normal, you put along the normal. Here is along this. And again, here you are also able to find. So you can see. So although one screw, in the concept you have one screw adjustment, but here you put two because it works only in one direction. So one is like a mechanical stop. So one helps in moving in one direction, other helps in moving in the other direction. So very nice mechanism. This is your main 4-bar mechanism or parallelogram mechanism. But you can see all the holes are oriented in different directions, and even the cut, they are made very difficult to understand. But if you are aware, you can decipher it very nicely, and you can find what is the mechanism hidden. And this is the mechanism here. So very nice. I think some of you can just take this example also, and we can work. It's a very good example. There are similar examples. I think maybe we stop here. Okay.